All right, so that's the idea. And any questions about this schedule right now? So I'm going to post the key to this new Exam 2 study guide. And it's very similar to the old one if you've already started it. And the key is very similar. It's just in a slightly different order. So today we're going to finish, let me just show you the calendar here. And let's get rid of this for a moment. And the idea is I didn't want to give you any homework here. I just want you to finish up all the homework at the end of the week, and then you can just start studying for the exam, or even start studying earlier. All right, and then we're going to have an exam review on Tuesday, and the exam's at 7 p.m. So what we're going to do this week is ANOVA for group means. So what is that? Let's get to that on the document camera. Okay, so, all right. So we've been doing analysis of variance for regression. And now we're going to look at this special case of analysis of variance for comparing group means. So remember, so what we're going to do when we compare two group means, the null was there's no difference between the groups, and we just looked at the observed difference minus the expected, which was 0 under the null, over the standard error for the difference. And we did that with a z or a t, right? And we could do that. I'm trying to make it more focused here. Why is that not doing well? Come on. There. Okay, and we could do that because remember when you have just two groups, you can boil the difference down to just one number, a single signed number. And so you could do a z or a t test. But what if we want to compare three groups on some quantitative variable? So remember, if we compared males and females, it was no problem doing a z or a t test. But what if we wanted to compare differences between exam scores between more than two groups? Let's say one thing I've been looking at is our freshmen, sophomore, juniors, and seniors. Are there any difference in the group means between their exam scores? Do freshmen do better or worse than the others, or seniors, etc.? And so then I have 4 group means that I want to compare, and the problem is, as usual, we can't boil down the difference between more than 2 groups into a single signed number. So what do we always do when we want to look at a whole pattern? We square the differences and sum them up. And we're going to get the test stat that's the ratio of 2 variances. It's going to be the F ratio. That's just like what we did for multiple regression. Okay, so we're doing the exact same thing here. So it should be really, really easy for you guys after you get the swing of it. And we're going to do the same thing, and we're going to end up with the F statistic, the F ratio. And if we have large N, that F gives you the same curve, the same shape curve as the chi-squared. Everything else being equal, if you have the same number of groups, just with a large N, you'll get the chi-square statistic, so we could use chi-square distribution, so we could use that statistic for large N. All right? And we're going to do this same thing we've done before. The main idea, you break up the total variation of the y's, we've been calling that SST, into the part explained by the model and the part missed by the model. This is what we've been doing. No different. It's just a special case of this. So we're going to have the sum of squares explained by the model plus the sum of squares that's left in the errors. And the null, as usual, so we're trying to explain the variation if I'm interested in exam scores and trying to predict them by the model of what year you are in school, right? That would be our model, that what year you are in school would be able to help us, the differences in those means would be able to predict the exam scores. And then you'd have some error around that model. And as usual, this error is just pure noise, right? And this model is noise, and maybe we're hoping a signal inside it. But the null says no signal, just noise. So as usual, we assess the relationship, the ratio of this divided by that, adjusted by their degrees of freedom, and when the null is true, that these are both noise, that ratio is 1. That's the F statistic, when the null is true. All right, so now, you might be thinking, how are we making a prediction just from group means? When we have regression, we had a regression line. And we looked at, the model was our regression line, and we looked at, from our sample, and we looked at the scatter around that line as the error. But now when we're comparing the averages to see if there are any differences between them, what is our model? Well, our model is the prediction based on each group's mean. So if you're a freshman, I would predict that my best guess for how you do it on the exam is the mean of the freshman. If you're a sophomore, I'd predict that my best guess for how you do on the exam would be the mean of the sophomores. And then the variation is just the spread around those group means. If there wasn't any, the errors, the noise part is how the spread around each group mean. So if all the freshmen did about the same, then there wouldn't be much error. But that's not the case. There's a huge spread around the freshmen. There's a huge spread in the scores around the sophomores and all of them. So it's not a very good predictor. So there would be a lot of error in that model. All right. So that's the same thing we did before, but I know that all this is going to make a lot more sense when we do an example. But I just want to clarify one thing I wrote here. I said when the null is true, the F stat, it's distributed with these degrees of freedom, we'll get to that. Its mean, I want you to know the mean of the F stat, when the null is true, the mean of the F stat, is 1, because when the null is true, it means our model's no better, it's just noise 2. So the ratio of those two is just 1. And the mean of the chi-square, just because it doesn't do that it doesn't center it at 1, it hasn't sort of normalized the curve, it's shifted over, so its mean is equal to its degrees of freedom. All right, and you're going to see these are exactly the same things we did before, but let's just jump right into an example so you can get the idea of what I'm talking about better. All right, so here's an example. Boy, is this hard to see, but you have your notebooks here. I'm going to zoom in a little bit. All right, so imagine that we did an experiment, 2 experiments were done. This is experiment 1 and experiment 2, okay? And they were done to compare the effect of 3 drugs. Drug A was given to group A, drug B was given to group B, and drug C was given to group C in both experiments. But they look different. Okay, now the null, what's the null saying? It says that in the population, this is just our sample, remember? In a wider population, the null is that the drugs are all the same, that even though we saw differences between the 3 people who took drug A, the 3 people who took drug B, and the 3 people who took drug C on some Y variable, some quantitative Y that measures how good the drug was, let's say, it's a quantitative measure, that in the population, there really isn't a difference. We just happen to see some differences in our sample due to the luck of the draw. That's a null. And the alternative, as usual, is no. They're not all equal, which means at least one of them is different. They don't all have to be different from each other, but at least there's one of them that's different, because they're not all. It's the same null and alternative we've had before with when we were comparing two groups. We'd say the two group means are the same in the population, even though in the sample they might look different. And the alternative was, well, there was only one difference there, so the alternative was they were different. But here, there's at least one of them is different. All right. So now we're comparing three means because we're measuring a quantitative y. Our y variable is quantitative, not a yes-no count. Okay? In all these ANOVAs, our y is a quantitative variable. All right, so now let's just do this one as an eye clicker. It says, in which experiment does it look... Okay, so there's two experiments. And let me just point something out before we do this eye clicker. That in group A, the mean was 1. In both experiments, okay? In both experiments, it was 1 on this measure of how well they did. And group B, the people who took drug B in this experiment had a mean of 2. And in this experiment, they also had a mean of 2. Okay, so these means are the same. And in group 3, this is a mean of -3 in experiment 1. And even though it looks like it's drawn on a different scale, it's the same number here. I just didn't have enough room to fit all these on this page. So they got the same group mean here for C. So let me write that down. In both experiments, have the same group means. So the mean, I'll call it y mean for A, is equal to 1 in both experiments. The mean of the y's for the group B is equal to 2, and the mean of the y's for group C is equal to -3 in both of them. This right here is just the overall mean of the 9 points. In each group, n is equal to 9 in each experiment. Okay? So of the 9 points, this is the overall mean. So the overall is 0 in both of them too. All right. So what I'm asking here is, in which experiment do one of the groups look different? So let's do this as an eye clicker. So let's go to here. And so that's the same as asking this question. Which experiment do you think provides stronger evidence that one of the drugs is different from the others? Just looking at it. This is just like a visual for you to look at. Just think. If you had that data, in which experiment would you be able to pick out, hey, I think one of the drugs is really different, at least one is really different than the others? If you had to make a choice between the two of them. Okay, so everybody had a chance to pick? All right, so let's see what you chose. And good. Most people thought experiment 1. And I would agree. And let's look at why. So let's go to the document camera and see, okay, I think experiment 1, because this group really looks different then these two, like everybody in this group, experiment 1, and most people probably saw it this way because it looks like drug C, group C, is really different in experiment 1. Like nobody scored above 0 here. They're all grouped down here, whereas these, there's a lot of overlap. Right? There's a lot of overlap, whereas everybody in group C is way down here. There's a little bit of overlap here, but not with this group. So, because it looks like group C is different. All right? You can't tell by comparing their means. Their means, look at the spread of the difference between the group means. How do the two experiments compare? Well, the means are the same. They're the same because there's the same group means. So the differences between these numbers are the same for both of them. But the difference is that they're really much less spread out here. Imagine if everybody in group A got a 1. And if everybody in group B got a 2, and if everybody in group C got a -3, then you'd know they were really different, right? So experiment 1 has smaller within group spread. So what the F-stat does is it compares the differences between the groups to within the groups. Between the groups, how spread out these group means are from each other is the strength of the model, but the strength of the error is how spread out they are within each group. Okay? So, under the null of no difference between the group, we'd expect that ratio to be about 1. That the spread of these would be no different. Think of it this way. Treat all 9 observations as coming from the same group. So if you imagine putting the 9 tickets in a box, shaking them up, and then randomly dividing them into 3 groups, the means of the 3 groups would differ just by the luck of the draw. But all individual responses would be governed by those same laws of chance. So there's no reason to think that people in the same group would be any more like each other than people in different groups. So that's another way to think of what the F statistic, why the F statistic would be 1 when the null is true. It's just what group you're in is just governed by the same laws of chance as the spread within the groups. All right, so before we do this, I think we should continue with that example we just did and now work out how to compute this F statistic. So let's just jump to page 176 because I think we have to actually work through the example before you understand it. So the null hypothesis, as we said, for when you're comparing these group means, is that all the group means in the population, where that's why we're using the mu, are the same. All group means are the same. So that's the same thing as saying our best prediction for the y's, for this quantitative y, doesn't matter at all which group you're in. We're just going to use the overall mean. Okay? The overall mean of all the y's. All the group means are the same in the population. We just happen to see differences in the sample means. And the alternative is The alternative hypothesis is we have this more complicated model that they're not all the same. And we can actually do better, make a better prediction of y if we use the group mean. For each of the 9 points, you say whatever group they're in, we'll use that mean, and that will make a better prediction. So for example, if we were testing whether, in our class, whether the differences that I see in the exam scores between freshmen, sophomore, juniors, and seniors, whether that's just due to random chance or not, the null would be that, yeah, it's just due to random chance. I might, that predictive, knowing what group you're in tells me nothing. Even though the group means are different in our sample, that difference is just due to random chance. And the alternative is, no, I can make a better prediction if for each one of you I use your year in school and the mean of that group to make a prediction of what you're going to get on the exam, rather than just the overall mean. Okay, so now we're doing the exact same thing we did before. Does using group means to predict y make a significantly better prediction of y than just using the overall mean? This is the same thing as, okay, so this is how this is the same thing we've been doing before, and this is just like chapter 27, okay? We went through this, so this is like chapter 27. We had the same split where we said, okay, you have the sum of squares total, which is just each of the 9 observations. In this case, we're going to do experiment 1 here. So we have these group means. This is 1, this is 2, and this is -3. And we have these 9 points here. And our overall y bar here, the overall mean is 0. So we're going to compare the total variation of these y's, all 9 of these points. That's what this part is. We can do it right here and compute it. We just have 9 points. So our sum of squares total is what? You just take, for each of the 9 points from I is equal to 1 to 9, you take the point, like I'll just write them down here, 1.5, 1, 0.5. These are all the points here. 2.5, 2, and 1.5. And in group C, it's -2.5, -3, and -3.5. So we have the 9 points. And the way we always do this, we say the deviations from the average. That's all this is. So we take the deviation. Well, the average happens to be 0. I made it easy for computational purposes. It's not always 0. The average is 0. So I'm subtracting off 0 from each one of these. And remember, if we summed these, just the way they are, we should get 0. The deviations always sum to 0, so that's why we square them. So this is just the first step towards finding the standard deviations. Okay, and then we add them up. So we can do that. 1.5 squared is 2.25. 1 squared is 1. 0.5 squared is 0.25. 2.5 squared is 6.25. 2 squared is 4. 1.5 squared is 2.25. Negative 2.5 squared is 6.25. Negative 3 squared is 9. And negative 3.5 squared is 12.25. We can add all those up, and this is our total variation of the y's. Okay? That's just like what we did before. It's a total variation from the mean. Now we're going to break them up into 2 parts. The first part is what's due to the model, our predictions. Okay? So we're predicting, remember what we're predicting here. We're predicting for each of the 9 points, we are going, our best, the model says we should predict the group mean for that point, for that. Minus, does that do any better than just using the overall mean? Okay? So we're going to do that for all of them. So for each point, we're going to predict. So for one, we're going to take our 9 points, and for all the points in there, all of them, we're going to say, okay, instead of 1.5, instead of using 0, for all three of these, we're going to use we're going to see how much better our model does. We're going to use 1. And for all these, we're going to use 2. This is our model. For all these, we're going to use -3 for all three of those points. So let's write that down. And how much does that? So for the first 3 points, they all have a group mean of 1, right? And we're going to subtract off our overall mean, see the improvement, how much better it does. And then for these, all in this group, what are they? All 3 of these points have a prediction of 2. And then all 3 of these points, for all of these, we're going to predict -3. And we're subtracting off. Now, it doesn't have to be 0. It just is in this case. But once you subtract all those off and you added those together, if you didn't square them, again, you would get 0, right? -9 plus +9. So we square all these. And this is our sum of squares model, which we call the sum of squares, the differences between the means. The bigger the difference between the means are, the bigger this is. So here we get 1 squared, 1 squared, 1 squared. 2 squared is 4. So we have 3 4s. And here we have 3 9s. So now we add these up, and we get 27, 30, 42. Now, remember how this sum of squares total is going to be equal to our sum of squares model, which we're calling the sum of squares between, plus our sum of squares within. So what should this equal? This we know should equal, if we do the arithmetic right, this should equal 1.5, because that's what analysis of variance does. And let's make sure it does do that. So what is this saying? This is the sum of squares within. So this is the part that I said was really small in this. These little differences around the mean, it's very small here compared to this part, which is very big. They're going to have, these 2 experiments will have the same sum of squares between, but this one's going to have experiment 2, which you're going to do as homework, is going to have a much bigger within group spread. You're going to do the same exact thing for experiment 2 that I'm doing now for experiment 1 on your homework that's due Wednesday. All right. So now let's see this. And so what should we do here? This says for all the observations, we're going to subtract off, this is the observed minus the predicted. That's our error, observed minus predicted. So for this group, we observed 1.5, 1, and 0.5. It's the same things we have here. But now we're just saying minus our predicted. And the predicted for each one of these is 1. Okay? And then we're going to square them. So what do we get for each one of these? 1.5 minus 1, 0.5 squared, so you get 0.25. This one was right at its predicted. 1 minus 1 squared, that's 0. And here we have 0.5 minus 1, negative 0.5. Again, if you didn't square them, these 3 would sum to 0. Okay, so now we square them, and we get 0.25 again. Okay, now we're going to do our next 3 points, which is 2.5. We're taking we're just looking at these little differences. Okay, so that's 2.5 minus 2.5, 2, and 1.5. And we're going to minus, their predicted is all 2. I made this problem pretty easy. They're symmetric around their means. They're not always, but I made it pretty easy. So this one, for us to calculate. So this is 2.5 minus 2 squared. It's going to be 0.25, 0, and 0.25 again. Doesn't always have to look like that, but. And the last one is these last 3 points are what? Negative 2.5, negative 3, and negative 3.5. And for each one of those, we're going to subtract off negative 3. Well, subtracting a negative is the same thing as adding a positive, so it's plus 3, and plus 3. And you can see that we're going to get the same thing again. 0.25, 0, and 0.25. That's because these happen to have the same spread, exactly in the same spread everywhere. So when we add these up, we have 6 times 0.25, and yes, it does check. So that's good. So that worked out great. Now the one that you're going to be doing for your homework, and maybe you can maybe I hope I finished in time. You could maybe even start it while you're still here. Is you're going to do this one, and you're going to see that you'll have these will be the same. You'll get this the same, right? Because they have the same group means. But the part that's going to be different, of course, is your total. You're going to have different numbers, much bigger variation. And these within, look at the spread around them. They're much bigger. They're like 5 instead of 0.5 for each. All right, so that's what you're going to be comparing. And look, we're looking basically, when we do an F statistic, we're looking at we're comparing the blue to the yellow. And if the blue's big enough compared to the yellow, we'll reject the null. Yes?
I have a question. How did you know like right away that it was 1.5 without doing
How did I know it was 1.5? Because remember the sum of, I'm using the basic idea for all analysis of variance that sum of squares total is equal to sum of squares model plus sum of squares error. That we're splitting that up. Good point, good question, just to tie it together. We're splitting up this variability. It's not quite the variance. If I divided through by n, it would be the variance. But this is the variability of the y's into 2 parts. The part we think that's explained by the model, those group means, and the part that's the error. Do you understand? Yeah. So that's how it should turn out. And so if it didn't, once I figured out one, if I asked you to calculate both of them, you could just give me that, but it's nice to check it to make sure you didn't make a mistake. All right. So that's the idea there. Now, this is probably, okay, so we did this. Now we can put this is extremely similar. I'll just take when I say look at chapter 27, what I wanted you to, just to refresh your memory, you'll see we did this when we first started thinking about analysis of variance. We did this whole thing. Here we have it. We explained it here, the same process, but we're looking at it in terms of regression, here in terms of a regression line with a slope. And so here's how we pictured this same thing, where this x-axis really had some meaning here. But it's the same idea, the model and the error, and then we did all this, remember? And then we put it into a ANOVA table. Now we're doing the same thing. It's actually easier with group means. So now we're doing the same thing here. Okay? And now, and just to, this x-axis here doesn't have any meaning. It was just a way to separate the groups from each other. There's no regression line here, right? Like in the same way. Okay. So now let's put this into the ANOVA table that we're used to. Okay? We've done all this, and I'll show you how the degrees of freedom match up and how you compute the F statistic from this. So let's turn the page to 177. So we're just going to fill that out, what we just got. Okay? So this is our sum of squares. Okay, here I have it. Sum of squares total. We got 43.5. And for our model, we're calling it sum of squares between the groups. This is the same thing as the model. Sum of squares model. Our model is called, the sum of squares is called sum of squares between. And this is our sum of squares error. And we're calling it sum of squares within the groups. So this is 42 and this is 1.5. All right. Now, that's what we know so far. Now we have to remember what we're doing here. Okay, we need n. That's the number. This is just for experiment 1. You're going to do the same thing for experiment 2. So for experiment 1, we have the 9 points. You'll have that for experiment 2 as well. And we have 3 groups. So G is equal to 3. Now, how many parameters do we have? So this is where it's handy. It's useful to think about how we're really building a linear model, a regression model, with a group predictor, which group you're in. And so the model, I don't expect you to understand this right away, but the model is really, we're making, knowing which group you're in. Our model tells us something about the Y, the 9 Y's. And let's just now, where does this come from? What does that even mean? So let's go back. I'm sorry I'm skipping around here, but I just realized that it would be easier to explain it this way. So if we go back to page 174, ANOVA for comparing group means is a special case of regression where the predictor variables indicate group membership. And the group means take the place of the slopes. So, so here we can rewrite our previous example with 3 binary predictors, 1 for each group. So what do I mean? All right, so this is a binary predictor. That's going to be what? 0. What would 0 mean? 0 if you're in A, and 0 if you're not in A, 1 if you're in A, and 0 if not in A. And this is another binary one that says 1 if in B, and 0 if not in B. And this says 1 if in C, and 0 if not. Okay? So each of our points is either a member of A, B, or C. And so if we wanted to have we could write this as a predictive model where we'd put what? If you're in group A, then these two are going to be 0, and our prediction for you is going to be the mean of group A. So this is always going to be the group A mean. And if you're in group B, I'm just using that last example where it was 1, 2, and -3. So that would be the group. This is obviously the group B mean, and that's the group C mean. And this is the group B mean. That's how I got those. Okay, so we could write it that way, and then you see we have 3 parameters. I'm just trying to write it this way so we can fit it into our model. We have 3 parameters. They're just the group means, okay? But the more typical way of writing it, more commonly, you choose one group as the baseline, and its mean is used as the intercept. And the other groups are represented with binary predictor variables whose slopes are expressed as differences from the baseline. So you'll still have 3 parameters, but you use one of the group means as the intercept. So for example, let's say we use group A mean here. Can you see, okay, so this, when group B is 1, this would be 0, and we want to get the group B mean, which is 2. So what would be in here? 1 plus 1 is 2. So this right here is just the group B minus the group A. And how about this? If you're in group C, then this one's 0, and you want to end up with -3. So this must be -4. So this would just be YC minus YA. In both cases, I'm illustrating this to you right now, just so you'll understand that in both cases, the number of, whichever way you see it, the number of parameters is the number of groups. We need this for our ANOVA table. So it's a really easy way to remember it and to understand it. So now that you have this, and this isn't going to be, I'm not going to ask you questions like this on the homework or the exam. I just want to show you how it can be written as a linear model. Okay? So now we're going to use that right here. That's what I said right here. So either way you could write the model, and either way just remember that it has 3 parameters. 1, 2, 3 if you do it that way, or 1, 2, 3. Okay? So this is the idea. The number of parameters, because we're doing the same thing. We're going to divide it up into the model, which has P minus 1, which is the same as G minus 1, parameters for the model. Right? The number of parameters is always P minus 1. So this is equal to what? We have 3 groups, 3 minus 1, which is equal to 2, right here, right? And then n minus P, n minus G, so n is 9 minus 3, so we have 6, and it's all going to add up to what? N minus 1. 2 plus 6 adds up to 8. These add up and these add up. This is how our usual way of doing an ANOVA table. Nothing new here. So now to get the F statistic, do you remember what we do? The mean square between, we just say the sum of squares between 42 divided by the degrees of freedom for the model. So this is our degrees of freedom for the model. It's equal to 21, and we'll do the same for the error. So we have 6 divided by, whoops, I did that wrong. Sum of squares 1.5 divided by 6. So that's 0.25. Sum of squares within divided by its degrees of freedom. And that ratio, 21 divided by 0.25, which is equal to 84, is our F ratio. So that's our F. Okay? And it should be, when the null is true, it should be 1. The mean of the F, when the, not should be, but the mean of the F statistic, when the null is true, is 1. And look what we got. So, and how do we get the standard deviation of the errors? This is a pooled, just, it's our usual. You take the square root of MS error. So that's the square root of 0.25. So this is, we're going to be using this a lot, and that is equal to 0.5. And what's R squared? Well, we can use R squared the same way we did before. Okay? The sum of squares model and the sum of squares error is equal to, how are you going to remember? Well, this is a tautology, R squared plus 1 minus R squared is equal to 1. Obviously, it's the way what we always do. But R squared times SST plus 1 minus R squared times SST is equal to 1 times SST. I can just write SST. So this is the model. Remember, this is what we've been doing all along. This is our sum of squares model, and this is our sum of squares error. Remember that? So I'll just put it right here. So this is equal to r squared times SST. This is equal to 1 minus r squared times SST, and it adds up to SST. So how do you get r squared? Well, r squared times SST is sum of squares model. Sum of squares model is r squared is just sum of squares model. Just 42 over 43.5. That's what it is. That's what it is. And that right there, I'll put it right down here, is equal to 0.9655. But now, we know that's significant. That's a huge F, but let's just go through it and look on the table. So what table should we look at? I don't have a space for it, but you're going to be doing this. This is your homework 18, first problem. You're going to have to do this and fill out this table. And then, how do the two p-values compare? Well, do you know, can you tell this is the better model? This is going to have a much smaller p-value than that one, but you'll see for yourself. Okay? Let's just do let's get the p-value for experiment 1. So, for experiment 1, our F statistic was what? Our F is equal to 84. So what are we going to compare it to? Well, how many degrees of freedom does it have in the numerator? 2. And how many does it have in the denominator? 6. So we're going to look at the F curve with 2 and 6 degrees of freedom, and we're going to compare it to some critical value of F at 2 and 6 and see how it compares. So why don't we look at a table, and the only table I provided you with is what? I don't think I have one for p equals a really small number here. Let's see. On your exam, you will get different ones. You'll get one for a smaller p-value. Here's 5%. That's the same as 5%. All right. So now, see how it says group degrees of freedom? So this is the same as the degrees of freedom in the numerator we've been always using. It's our model degrees of freedom. And that is 2, right? And so we're going to go down here to 6. So our degrees of freedom here was 6. So it's going to be right here. We're looking at this and this one. So that's our F star, 5.143. All right. So that's what we're going to compare it to. So that is 5.143. And that's at what? P equals 5%, or alpha equals 0.05. So the curve would look like this. This is much bigger, much, much bigger. So our p-value is going to be much, 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 much smaller than 5%. Much, much smaller than 5%. And if I wanted to draw it, I can draw it here. I'll just draw the curve. It's going to be really asymmetrical, like this. And right here, I'll draw F star. That's 5.143. That's our F star. And that means from here on in, all this is what? 5%. All the way to the end. Now, where's RF? We have to draw it to scale. RF is off the page, but I'll just draw it way down here. This is where RF is. That's where 84 is. So our p-value is just the tiny, tiny, this is all 5%. Blue, keeps getting smaller, 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 smaller. Ours is that speck beyond that. That's why it's so much less than 5%. Our p-value is so tiny. P is almost 0%. You'd have to use a p-value calculator. So what would be our conclusion? Just what you thought, at least one of those. So we would reject the null. So our p-value is way less than 5%. So we would conclude, so our conclusion from experiment 1 is to reject the null and conclude that not all those means are different in the population, that at least one of the drugs is really different. We don't, that they might all be different, that at least one drug is different, has a different mean in the population, that the mu in the population is different. From our sample, we can conclude that. So, any questions on that? You're going to do this one. I think you know what to do. Just do the same exact thing as we did here. Now, I want you to, before we look at the next page, I want to go back to the summary here and just make sure that we understand what's going on. So now we're back on page 175, and it says, ANOVA for comparing group means is an extension of the two-sample Z or t-test to 3 or more samples. Remember, when we have 3 or more samples, we can't use a Z or T. Okay? We actually could use either if we just have 2 samples. You could use the Z or the T, just like, or the chi-squared, or the F. So ANOVA is a special case of regression where the predictor variables are group membership. We use the same, this. Okay, so this is the part I want you to look at. All right, so for regression, this is what we've been doing. Right here, we've been doing this. And for large N, we've been getting this. For ANOVA, this is so confusing because this term ANOVA refers to 2 things. We're doing ANOVA here. It refers to, when people say ANOVA, they usually mean comparing several means. But it also refers to the procedure of partitioning the variance into 2 parts, analysis of variance. And that procedure is done for both comparing means and regression. So it's, when people say ANOVA, they usually mean this, but also this whole thing is it's also, we're doing ANOVA when we partition, whenever we partition the variance and compute these things. Okay, so how do these differ? What's the difference? Just the terminology here, just the terms we're using. Notice that P and G are the same. That's how you can remember it well. And sum of squares between is the same thing as the sum of squares model, sum of squares error, sum of squares within. Okay, so now that you know that, we can do our next example. All right, so this is, this ANOVA is very useful because often you want to look at group differences. So this is data from a while ago. On a scale of 0 to 10, rate where you fall. 0 means you strongly favor gay marriage. This is from 2014. And 10 means you strongly oppose it. So I asked this of 858 Stat 100 students, and I got these different means. Okay? So are there differences between the ethnic groups on their attitudes towards gay marriage in the wider population? You imagine that they're chosen from some wider population. So here you have these 5 histograms with their different means. And it looks like there's substantial differences. It looks like these are the people who are most pro-gay marriage, and this is, right? No, these people. So who are they? So this is Hispanic. The most pro-gay marriage and the most anti is black right here. And this in 2014 in Stat 100. So the question is, So we get these different averages, and this is the histogram of how they responded. And it looks like there's substantial differences. But so the idea is this just due to chance variation? If we randomly divided people's responses into 5 groups, would we get differences this big or not? So can we predict a random person's attitude toward gay marriage better by knowing which group they're in? So I got the R, the correlation between the predicted ratings based on ethnic group membership on the 5, just assigning that would be their predicted. That correlation between that and their actual ratings is 0.1920. That's fairly low, but the numbers are high, so is it statistically significant? It's 0.2, so almost. So now we're going to just quickly, instead of doing the whole chart, and we certainly can't compute SS within by hand, so we're just going to use R squared. Okay? So what's the appropriate significance test to test the null, that all group means are the same? We just happen to see small differences in our sample. Well, the first thing, we have 5 groups. G is equal to 5. So that alone should eliminate Z and T. You can only use this when you have 2 groups. You can't use it for more. Okay, so how about the F test only or the chi-squared? What's our N? Our N is really big. From the previous page, our N was 858. That's a really big N. So I think we can use either. So either, these are essentially the same for very close to the same for big N. So our answer would be this. Okay? Now, so the null hypothesis is what? The null hypothesis is that all group means are the same in the population. So what would it be? Mu for our best prediction, all group means in population are the same. We just happen to see in our sample, all group means in population are the same. So what's the alternative? Which one? Do they all have to be different, significantly different from each other? No, just they're not all the same. At least one's different from the others. So now we're going to compute the chi-squared. Oh, that was supposed to be a clicker question. Darn. Oh, well. I'll ask you one right at the end. I'll ask you a different one. Okay, so now compute the chi-squared. So chi-squared, you should know it by now. See if you can remember it. Remember, it's R, I'll start it. R squared over 1 minus R squared. Times what? It's so easy. Just times N. That's it. Okay, so we're just going to compute that. So we were given from the previous, oops, it's right here. Okay, so we have 0.1920 squared over 1 minus 0.1920 squared times 858. And even though that's pretty small, this ratio right here, we have a big N, so we get 32.84. Okay, now, do you remember how many degrees of freedom for the chi-squared? Degrees of freedom for the chi-squared is what? It's the number of parameters minus, did this go out? Did it? No, it's good. It's the number of parameters minus 1 always, which is the same as the number of groups minus 1. So that's 5 minus 1, which is 4. Okay, so we'd expect, when the null is true, we'd expect to get the mean of the chi-square statistic when the null is true is 4, and look how much bigger this is. But let's compare it. Looking at the chi-square table, critical value at p equals 0.05. Okay, let's look at that. So, let's look at our chi-square table. All right, degrees of freedom is 4. At 5%, it's 9.49. But let's look at ours is even bigger. Let's go, okay, so 9.49 is what the question asked, but it's going to be smaller than 5%, our p-value. Will be smaller than 5%. It's going to be it'll be smaller than 0.1% because our statistic is bigger than 18.47. So let's use that instead. Let's say it this. All right, so r chi-squared is equal to 32.84, which is much bigger than the critical value with 4 degrees of freedom equal to 18.47 at I want to go p equals 0. Usually it's alpha equals 0.001, or I went to p equals 0.1%. That's how it's usually written. Okay? 0.1%, isn't it? That's what
I mean, like, why are you changing the critical value? Because I thought it's 5%.
why am I changing? Good question. Why am I changing? Why aren't I just giving the critical value for 5%? That was what the question asked. Yeah, that would be the answer. But I'm changing it because we want to use this table. We have more information. We want to say, wow, the p-value is even smaller than that. From this table, we know it's not only less than 5%, we can give more information and say it's even less than 0.1%. That means there's really, really strong evidence to reject the null. The smaller the p-value, the better your model is. Okay, so we're going to really reject it big time. So that's why I changed it to that. When I wrote the question, hadn't done the calculation. Okay, so that is equal to, so this is at 0.1%. So since this is bigger, our p-value is what? Our p-value is a lot smaller than even 0.1%. Okay, does that make sense? Now to compute the f. What's the f? The f is the same thing. It's r squared over 1 minus r squared times n. Just start off the same way. But now you have to tweak that n, right? So you say n minus p, but now it's n minus g. And then we divide by these numerator. Once it simplifies, the numerator degrees of freedom is g minus 1. So we have the same thing. 0.1920 squared over 1 minus 0.1920 squared times 858 minus 5, which is 853, over 5 minus 1, which is 4. And so then I get a statistic that's going to look very different, but once the p-value is going to be very much the same. It looks like 4 times less, but that's because this one's centered at 1 and this one's centered at its degrees of freedom, which is 5. So how many degrees of freedom for the f's numerator? That's p minus 1, g minus 1, that's 4. And for the denominator, n minus g, which is 853. And now we're going to have to look at, so our f statistic, our f stat is equal to 8.162. And it has degrees of freedom 4 in the numerator, 853, right? Our chi-squared, this was 4 too. And we're comparing it to the f star at 4 and 853. Let's look at our f critical value here. So So how are we going to do this? So we don't happen to, we just have the 5% one. So we'll just look at the critical value here. And in the numerator, we have 4. Whoa, we don't have, this doesn't go up high enough. I'd have to give you a different table. Let's use the p-value calculator. Okay, so we'll just go over to the PC and we'll use that instead. Let me just ask you another question. What should I ask you? Don't have a question. Are you going to start the homework right now? Are you? Do it today and come to office hours if you need help. So I'm just curious, do you think you're going to start this homework? Say yes or no. Yes, A is yes, B is no. I strongly recommend you start it today, but I'll be in office hours today and tomorrow if you need help. So just click anything, A or B. And let's just give you credit here that you stayed, and then I'll just show you this is the last thing we're going to do is just look at the p-value calculator. And if you want to stay right after we finish that and do your homework right now, start that. You could probably get that first problem done, and I can help you with it if you need it. All right, so I've just clicked something, stop it, and I don't need to see what you wrote. And then I'm going to go back to the document camera, and whoops, the p-value calculator. Let's just go back to this, and let's just get out of here. And just look at it. Okay, so here we are. You just go to the calculator here, and we're going to just go to the F distribution. And our degrees of freedom is 4 in the numerator, 853. 853. And our F statistic was what? 8.162. So let's see what we got as a p-value. It's very small. Very tiny. If we wanted to figure out the critical value at 1%, why don't we do that? So we'll figure out the critical value at 0.1% like we did for the other one. And now we'll compute the F. So it's 4.662. All right, we might as well write that down. So let's go to the document camera. So this is equal to 4.662 at, same thing we did here, at 0.1%. And since this is pretty much greater than that, our p-value is much less than 0.1%. Okay? So again, from both, we reject null and conclude that not all those, at least one of those, not all those group means, not all mu sub i's, what are the, mu sub i's are the same. In other words, at least one is different in the population. This one is different. Okay? So it reflects some real difference in the population. And the next thing we're going to do, next time you're going to see is, now how do we tell? Once we did that overall test, we're going to look at how do we know which one's different? Which one is different? How are we going to do that? We're going to look at pairwise differences next time for that same example. Okay? So read the summary, and that's it.